Nice to see you all here. I am going to talk about chips, in my opinion, the most delicious kind. I'm going to talk about a little bit how they're made, how I design my own, and how you can too, and how surprisingly easy it is all of a sudden. So, yeah, our lives are filled with smart everything, and basically this has happened because of the invention, miniaturization, and mass fabrication of amplifiers and switches, basically transistors. And I've done my part, in, like many of you, in making the smartening of everything by designing circuits and PCBs, and that's where I spent most of my time doing stuff like that. I got to do all of that thanks to my position as co-founder of Psychogenic Technologies, where we go from dreams to reality by doing architecture, prototyping, small batch assembly, and stuff like that. I also post on my YouTube channel stuff that I find particularly interesting, so if you're curious about that, be sure to check it out. It's kind of fun. So some of the words I love to hear the most are make me a widget, and there's lots of steps in there, but one of them, the important ones, is selecting components. Now, what we're doing when we're creating a circuit is taking one of a vast array of everythings and designing something that'll do the job we want under the constraints of whatever it is that we're dealing with. One of our main tools are integrated circuits. And so, I mean, they have the most punch per millimeter and the most flexibility because inside of these little black boxes, there are patterns in magic sand that somehow just do all these different things. Now, I got curious about that. What are all these transistors? Now, the transistors are the most manufactured human artifact ever. This was an estimate, 13 sextillion, and that's actually a number. It sounds like gazillion, but it's like something with 21 zeros. This is an estimate, of course, but it is the most produced thing that we ever did, and it's because they're so useful, depending on how you configure them, basically. So, can I not stop this video? Please move forward. I guess we'll watch the end of this. So they're manufactured in many steps, basically, through these things that, like the PCBs are done in what we call fabs. They call them foundries when it comes to making the actual chips. The process is many, many, many steps of basically something similar where you have masks and etching and stuff, but at a much smaller scale. So I was curious about this stuff. I was curious in a general way, but I also got really curious when I worked with teams that were doing their own application-specific integrated circuits. Now, they did it because they were not necessarily going to produce millions of them, but their needs were so specific that there wasn't anything on the shelves there that would meet the power requirements or the weird things they were doing, like backscatter and analog neural nets and really cool stuff. So if you're curious too, or if you want to make a bunch of cash playing with this stuff, we actually were looking for analog IC designers, and they are hard to find. So if you just play with it, that'll be fun, but you can actually make a career out of this stuff pretty easily. Now, there were two big obstacles. The first one is it's a whole nother world. You're doing circuits and stuff, and you get it. You read the data sheet, da-da-da. That's fine. But this is another universe. And depending on how deep you're going, the tools you're going to use are different. The considerations you have are different. So there's a lot to learn, and it was kind of hard to figure out where would I start. But I can deal with data sheets and technical info. I'm sure you can too. The real huge barrier was getting into there. Now, the PDK, the process-specific information that you need to make the design, is so bound to the foundry's process that they're really conservative in how they let it out. So it costs a lot of money. There's NDAs. There's a whole lot of barriers to getting into there. Cost is huge, but even if you have the money, it's a lot of steps and a lot of pain. So at that point, I was like, well, it's interesting, but maybe it's not for me. And then something happened. A few years ago, Tim Ansel, when he was at Google, actually pushed a whole bunch to get Google to get Skywater, which is a foundry in the United States, to actually open up their process. And they did. And so that meant a lot of stuff, but the short version is that Google had this, they needed engineers that knew how to do this stuff, and so they opened up the process and they made this shuttle, okay, this lottery, where you can design your thing, and hey, if you're lucky, maybe you'll even get your chips produced. Cool, but you end up doing the design and then it just doesn't happen. It's kind of sad. So later on, Matt Venn there in his iconic yellow hat decided that he was going to try this out because it's a whole new world of interesting possibilities. And he started teaching other people how to do it. This was in the days of the lottery. And then he hooked up with Uri Shuckhead, and they started something called TinyTapeout. And the goal there was to offer the possibility of doing your own designs, guaranteeing a spot. Now, still the barrier, number one there. So they created TinyTapeout, and that's basically how I've done all these chips. So this is a wafer. It's basically a slab of silicon doped in a way, and then what you do is, similar to the PCBs, you'll have a mask, you'll do some etching, you'll dope these parts, you'll put an insulator, hundreds of steps. The point is, the process and the work is kind of expensive. The masks, there are many masks, and we're talking about nanometer scale things here, right? So super expensive. So the way that people found to reduce that cost is to do a multi-project wafer. So, okay, it'll cost $300,000 to create the masks and put this through the process, but I don't need the whole chip right now. I'm doing prototyping. I'm trying out my design, whatever. So I'll take one of these slices, and you take that slice, and we'll split the cost. So that's what TinyTapeout did. They take one slice from a multi-project wafer, and then each one of those little squares in there is one chip. Well, let's do it further. Each of those chips ends up having a bunch of little tiles in it. So you've got the pad ring there, which is basically the way you connect to the outside world. And inside of there, you've got a bunch of little squares. And each one of those squares is a project. So we cut the cost by getting a multi-project wafer and taking one slice. And then we cut the cost of each chip by having hundreds of projects on one chip. So, okay, that's how you reduce the cost. But how do you actually make a project? Now, there are actually three approaches to this, and that's the advantage of that is that you basically have access to the whole stack. If you're a beginner, you can start today, and if you're an expert, you can go as far as you can go. So we actually managed to have workshops where in 3 hours, we had people coming into the place with their kids, with tweens, getting to tape out in 3 hours. Now, yeah, I don't know if you could read my subtle expression there, but it went pretty well. That was the first one I hosted. I think it was at Hackaday. And so, okay, digital logic. So if you drive those transistors real hard, you're basically going between zero resistance and infinite resistance, right? And depending on how you pattern them, you'll get logical operations. Both of those switches need to be on to go through, so that's an AND. One of these switches is on, it goes through, that's an OR you can have a NOT, blah, blah, blah. So way down at the bottom, there's transistors that are organized physically, and then you think of them in terms of gates. And with these gates, these are logical operations, you can basically express any propositional logic. Anything you can say, if this and that, or this and that, that can be produced. And then you can have clocked versions, which are synchronous logic, which is a bit more complicated. But the point is, the TinyTapeout uses Walkwe for this. So it's basically an in-browser editor where you can set up your gates, do pretty much whatever you want, and because in the end, a chip is just a bunch of gates, a digital logic chip, well, there is no limit. Now, Walkwe is actually very useful in other regards. You can, it's good. I use it more for doing anything with Arduino or ESP32. I did videos about that. But in essence, you can sit down, log into the site, create a design of any complexity, although it's limited in practice because you're not going to end up making a CPU in gates. That would be insane. But you could in theory. So you design this circuit, and then that's it. You get a project ID, and from there, you clone this template. You edit one file, put in that project ID, push your commit, and GitHub Actions will take that circuit, harden it, and then it'll basically be includable into one of the chips, into one of the tiles. So I didn't actually produce a project like this, although I did help some people do it. When TinyTapeout 3 came out, that's when I did my first design. Now, way back in the days of TinyTapeout 3, this was a whole year ago, these are the projects, okay? And they were daisy-chained. So, okay, I want to talk to my projects. It's number 17 over there. Well, how do we do that? Well, the way TinyTapeout 3 did it is that all the inputs would go through each project addressed to project 17, and then it would receive them, and the outputs would come out the other end. So it worked, but it was kind of slow. And that's the demo board we did for it. Basically, the ASIC is on a carrier, and you have this extra functionality where you could select your project and see the outputs on a 7-segment LED or use the PMODs to do whatever. So in that context, I needed, because they were all daisy chained, the actual speed to get through there was kind of slow. We're talking kilohertz here. So in that department, I was like, well, what could I do that's kilohertz? And I thought, maybe something audio, and I did Project Neptune. And Project Neptune is basically just a frequency discriminator, but it's the world's most extreme guitar tuner. And so the idea was to take some input, count the ticks, and then see, okay, well, this is an E, or this is an A. And so, whoops, went too far there. How do I back up? Okay, well, anyways, the idea is this. Instead of doing it with walkWe, just a gate at a time, I used an HDL. So an HDL is a hardware description language, and you can either use, venerable Verilog, where you're basically describing the hardware. Verilog is not so much to my taste, so I used Amaranth, which is basically Python instead. And what's interesting, it's kind of meta with Python, because at least with Amaranth, what you're doing isn't, you're not writing the code, you're writing the code for the system that will describe the hardware in Verilog and then be translated. So it's a little bit meta, but it's also super flexible. So I took my super design there on the left, I converted it into something that would describe the hardware. I used a state machine, so it's a little bit, it's not completely leveraging the advantage of the hardware. It's still thinking a little bit like a programmer, algorithmically, one step at a time, but it worked out pretty well. I finally got the chips now, but because it's digital logic, I actually managed to test it all on an FPGA. And so this gives you, if you have done FPGAs, you have a leg up. You can go really quick and design your own ASIC. If you have not done FPGAs, you can play with this stuff, and most of the stuff you learn will be translatable immediately to FPGAs. So that's kind of cool. So this is what my design looks like in the end. This was one square, and you can see on the top layers there, so those are the actual standard cells, the little pieces of transistors organized as gates. And on the top, all that squiggle was basically the routing, the metal layers. So you have 5 metal layers that what you're doing is you're describing it, it becomes Verilog, and then the machine just places everything for you. It's like an auto router from hell. Oh no. The lessons learned, yes, all the FPGA tooling and stuff, it's basically the same. So if you know one, you can apply it. If you don't, it will apply to both worlds. You also get to learn a little bit about MOSFETs in general, the idea of standard cells, because when you say this and that, well, the PDK has a piece, the standard cell, this is a perfectly optimized for the process, 2 gates, and all the standard cells have this shape where they can be injected pretty much anywhere. Power will come in, and the outer router will figure out how to do that. So I used the Zero to ASIC course to get through this. You don't actually need to, but it's a nice way to have a clear path from, I don't know nothing, to actually having a design. However, if you don't want to do that, I've got videos. There's tons of ways to do this. You can just go on the TinyTapeout site, and there's a bunch of instructions there. So that was my first project. Then came TinyTapeout 4 and 5. Now, a couple of things changed here. We got more I/O. It used to be 8 in, 8 out. Now it's 8 in, 8 out, and 8 bidirectional, which is pretty cool. It also got a lot faster. Instead of daisy chaining the input and output all the way through, now you can say, I want to talk to project 17. The MUX just clicks everything there, and you get all the speed, only limited by the GPIO, basically, by the pins on the outside. So it all goes through there, straight to your project, and out from your project. So that's really cool. The thing with the MUX is it's built in there, and it's not using an MCU or anything like that. It's kind of dumb. So it's basically 3 lines that you have to drive somehow. So in order to get this to work, to be able to say, I want to select project 17, we actually did, this is Yeah. Oh, yeah. The other thing is we got access to more tiles. So instead of having just one square, you could have more. And I ended up making this monstrosity, which was a SHA-256 encoder, and it's 8 by 2 tiles, and it's gigantic because I was completely naive in how I was treating the memory. So it's just a bunch of flip-flops. It took a lot of space, but it's possible now to have a full CPU in there, no problem. So in order to drive that mux, this is the demo board and all the blah blah I put about it. But the important thing is there's an MCU on there, and we needed an MCU. So, well, let's use an RP2040. It's $1. It has incredible power. It talks USB. So since we had to drive the mux, well, I just tied it to all the I/O and to USB. So now, when you're selecting a project, you can actually go through the Commander app, which is your browser straight to the demo board. It connects to it, and you can control stuff, choose projects, and do things. Or you have a REPL, a MicroPython environment, where you can basically do anything. You can script and run your tests, or talk to your device, or simulate SPI flash, or do whatever you want, really. It's kind of amazing how powerful it is to have that on the MCU. The other thing is that little board I'm holding there is a Simon expansion. The PMODs let you do pretty much anything because you're able to talk to all the I/O. I select the Simon project there, and I'm playing Simon on the ASIC through this PMOD. And so that gives you a lot of flexibility in terms of doing extra stuff on the side because, okay, I have my project that does whatever. Well, I just plug in some extension board to be able to connect it in some custom way that makes sense. So that's pretty cool. So, oh yeah, about my tuner. So my tuner was digital. It was a pure digital project. I needed a way to actually digitize the input from the guitar and get it into there. So I ended up playing with some analog circuitry to do a front end. And actually, I have a board for that, and I have yet to assemble it. But the point is, the analog front end had to be separate because this was a pure digital project. Well, with TinyTapeout 6, suddenly we got access to analog. Now the reason we couldn't have analog before is that you can do anything you want in analog. You're basically just drawing. So I could have shorted out something or just rendered the whole chip broken for everyone. Now each of those little squares is power gated. So if I turn on my project, it's on. Otherwise, it's just dead sand. So there's no more danger there. So what happened was Matt actually did, I did a beta run of the analog Zero to ASIC course. And so we actually had some material to get started and access to some experts to answer our questions, which was really great. Now, the thing, if you're doing analog, this is the extreme level, right? You're used to doing a PCB with KiCad or something, well, you'll use schema. In this case, you use XChem. Why? Because it's a little bit more specific. When you choose a MOSFET, when you're down in analog land, you're going to say, I want an NFET, low voltage threshold, okay, you choose that. But then you set the width and the length, and you set all these parameters. And so you're at a whole other level of complexity because you're deciding how much current's going to go through it, what its capacities are, by determining its physical geometry, the number of fingers, the multiplicity, which is basically how many you have in parallel. Then you use magic to do layout rather than PCB new. Pretty much the same idea. This software is a little bit alien, at least it was to me, because it's pretty old school, but it's also pretty powerful. Magic can actually take this layout. See, those squares are different MOSFETs with different geometries. The ones on the right are capacitors, very small capacitors, but whatever, I needed them. And so Magic can take this, which is just a drawing like a Photoshop drawing, layer by layer, but each layer means, okay, this is going to be a metal or insulator or whatever it's going to be. And it can take this and then translate it to not just a net list, but including all the parasitics. Because if you have a piece of metal there, well, it's got capacitance to metal that's nearby or to the substrate or da-da-da. So you can do some extraction and then see, okay, this is the actual circuit I have, all the transistors, all the bits, but all the parasitics as well. And from there, so I started with just copying out a comparator that the guy who did XChem did. And so I did it just to learn how to use XChem. And then I had a comparator, so what am I going to do? I ended up doing an analog to digital converter. So the awesome thing here is because it's completely flexible, you can do your digital thing like you did before, but then you take that block, this is going to be my control, and what it's doing is it's controlling a DAC, and then it's reading the comparator and doing a little bit of math to output, you know, the final value. And so that block of digital stuff, the one on the right there, I just popped in, and all the rest is basically hand-drawn. This here is an R2R DAC, so it's just a bunch of resistors put in a way that you can set the bits and the analog comes out. Here's the comparator with muxes and stuff, and a capacitor that is just 4 plates in parallel like that. So that was a lot of fun, and the thing is, this is level 1 basically. You know, this was my first circuit. I didn't really know what I was doing, but it ended up, so because I could extract all the parasitics and everything, I still don't have this. It's going to take a few months before we actually get those chips in the hand. But I managed to do, it's kind of hard to see here, but this is a gate level simulation where I took the parasitic extracted everything, including the digital side, and just ran everything like analog. So in Spice, I put a clock that was 5 megahertz going okay like this, and then I simulated everything for those purple lines are different voltage level inputs, and then the yellow is the DAC calibrating and then going, okay, it's lower, oh, it's higher, oh, it's lower, it's higher, and then zooming into the actual target. And I don't have any proof as of yet, but it does seem to be working pretty well. This is impossible to see right now, but the point is I checked the results, and I was expecting like hex 10, and I got 11. Hex 20, I got 20, 30, 31, 40, 42. So it's actually homing in within the resolution of, you know, the 8 bits I have in my DAC to the value, up to maybe the last 3. The common mode rejection up at the top is pretty awful, but otherwise it actually works, which is pretty amazing. So with this analog stuff, I basically learned that you can get started. It took me basically 2 weeks to go from I don't know anything to having a mixed signal design on a chip done, which is, I find, impressive because it's a whole world. And it works. It seems to work. However, the amount of things that, I mean, if you can look at any particularity, the configuration of a MOSFET, you know, you have a gate and a drain and a source. Well, the gate can be 1 wire or it can be 4 in line. This is the number of fingers. Well, that changes a whole bunch of things. It changes the internal resistance of the gate, changes capacitance stuff, and blah, blah, blah. My point is, no matter where you look, it goes super deep. So you can become an expert on pretty much anything just by playing with this long enough. I did simulations of different things like the trace width versus capacitance, played with diodes, played with a bunch of stuff. It's really interesting. Anyways, I put up a video that goes through the process, goes in a little bit more detail than this for the analog side. I also had an interview with Robert Ferenek, and we basically did a walkthrough, which was exciting because it was live, and we're just doing an inverter, you know, the hello world of anything. And of course, while I'm doing this, and it's kind of live, hit this weird I'd never seen before, but resolved it in the end, and so that gives you a real taste of how it works. So the 3 approaches are walkwe, which is for beginners. The advantage is that there's 0 install. You do nothing at all. You just put it in your browser and then GitHub, and then it's done. The disadvantage is that you're doing it all at gate level. So there's a limit there. HDL, you can use the HDL of your, well, not necessarily of your preference, it's Verilog, but anything that gets to Verilog will work, and you can do anything digital from there. I mean, processors, really complicated stuff, they're all done in HDL. So there is no limit to how far you can go using the HDL approach, and the fact that you can have many tiles in TinyTapeout gives you the flexibility to do any level project. The only disadvantage is that these are pure digital, so that's where you're at, you're doing digital. And finally, you have the analog and mixed signal. Then you can leverage all the digital stuff to do your control and whatever, but at the same time, the sky's the limit because you can basically draw anything. Normally, you'll use a MOSFET that's from the standard library and just customize it, but in theory, you could even draw those. So the level of experimentation you could do is pretty much infinite. And the turnaround for ASICs isn't super fast, but the idea that you can get this on your computer. I installed a virtual machine that Yuri did for the analog stuff. So in one evening, you download this thing, you open it up, it has all the tools, and you can basically start doing analog and mixed signal designs, which I find pretty amazing. One of the lessons about this for me was that one of the big obstacles was cost. Okay, cost was a huge barrier, but that barrier is gone in this case. However, it's not just about that. The openness actually does a few things. First of all, it makes it that it's possible for anyone with a computer and the internets to start playing. But the other thing is, the DAC I did, the ADC I did, well, it was a comparator that I kind of was inspired from Stefan Schipper's. The DAC was something that Matt did, and I tweaked it a little bit, but I just put it in there. So you get all this cross-pollination, and we start playing and we're learning together. I mean, we're all in the Discord. There are people who are beginners, like me in this, but there are guys who have 30 years of experience there. And everybody's doing their own little thing, but then they all mix and match. I used his DAC. I've been playing with an op-amp from someone else, and that's one thing. Finally, eFabless, who organizes these shuttles with the MPWs, they basically organized something called Chipalooza, which was an analog and mixed signal design challenge. And they're basically have these objectives, okay? Design a bandgap reference, design an ADC, design these things. And so they're opening up these prizes, but one of the conditions is basically that the idea is that this thing will become a Lego block. You need a bandgap reference? Here it is. And so you can just use them, plug and play, or you can learn from them because they've had someone in the loop there giving them feedback and tweaking it and making it better because they want everybody to be able to use this. So it's the equivalent of IP, except that it's completely open. So you can see how it's done and not have to think about it if you don't want to, just plug it and play. So that's pretty much it. You can start wherever you are with this stuff. So my invitation is to come in and join us and play. If you're a beginner, follow the Walkwe tutorials. Basically, you can start with what's a gate and get to doing your own design. Probably, if you're here, you're not a complete beginner. The HDL is right there. If you've done an FPGA, you can do an ASIC right now. TinyTapeout 8. There's still a number of weeks before the deadline, and the really great thing is, unlike the lottery, if you want to play, you can play. The tiles are something like, one square is something like 160 UM by 160 or something like that. One square is something like $50. And so it's amazing. Everything that used to be, we were completely locked out, now it's opened up. And I feel like we're a little bit like, although we've been doing transistors for a long time now, this is kind of a renaissance or an explosion of creativity because suddenly everything's been opened up. It's a great time to not just learn, but to contribute and make a mark in a world that will exponentially increase just because it's open and we're playing together. And so that's it. If you have any questions, let me know.
In that size, how many gates do you get in that tile?
For one tile, the estimate was about 1,000 gates. There's some wiggle room in there, but what's surprising is how much you can do with, even if it was just 1,000 for real, there is a lot of space in 1,000 gates. And you can actually, if you work at it a little, you can squeeze things a little tighter. So you saw the Neptune thing. It's not the most complicated thing, but it wasn't even using half of one tile. So.
On the DAC, when you were showing the different values, what was going on at the higher voltages? It seemed like there was less resolution.
Yeah, the comparator just messes up super bad at that level. So when you're, let's see, where is it? Is that this? Yeah, here. So up at the top, the comparator, if you see here, If I had it live, we could see this better. But at the top, when you're up there, the common mode rejection is awful, and the comparator, because you're supposed to have the comparator and then boost it with an op-amp afterwards. And I was like, man, I don't have time for this. And so what it does is go, and it's just acting all fuzzy and weird. And what I end up getting when the two voltages are high like that is ones. I just get F. So those three, pretty much, yeah. Something to fix in the next iteration. Is that time?
It's time, yeah. Thank you very much. Big round of applause. And if you do have other questions and want to take the conversation, please just step right out here. We're running a little bit behind, so trying to keep things on schedule. Thank you.